Now we are going to continue study of carbonyl compounds. So we are going to examine carbon nucleophiles, and we'll be looking at organolithium, organomagnesium, and organocopper compounds. We'll also look at sp carbon nucleophiles and at Wittig reaction. Organomagnesium compounds, or Grignard reagents, and organolithium compounds are prepared in transmetallation reactions. So here, highlighted in yellow, are organomagnesium compounds. They are called Grignard reagents after Victor Grignard. He actually did not discover them. His PhD supervisor discovered them, that was Barbier. But Grignard figured out a way to make them in good yield and reproducibly. Paul Barbier found this reaction, but he was doing reaction in hydrocarbon solvents, and they are not soluble in carbon solvents, so yields were very poor and reaction wasn't very reproducible. Victor Grignard figured out that if reaction is carried out in dry ether as a solvent, and most commonly we use either diethyl ether or tetrahydrofurane, so in ether as a solvent, Grignard reagents are soluble, and so reaction proceeds very well in really good yields. So this is metal halogen exchange reaction. Typically we use alkyl bromide, but alkyl iodides are also very reactive, and sometimes we can use alkyl chlorides. Of course, alkyl fluorides do not work. It's only chlorides, bromides, or iodides, and chlorides are most commonly used because that's the best compromise between reactivity and cost. As you can see, reaction is formally an insertion of magnesium into carbon-bromine bond. So organomagnesium compounds contain carbon-magnesium bond, and we'll examine the nature of that bond a little bit later. But that bond is polar covalent, and carbon is the nucleophile. Alternatively, a little bit more recent reagents are organolithium reagents. Organolithium reagents are prepared by lithium halogen exchange, and these compounds are soluble in hydrocarbon solvents, which means that reaction is usually carried out in hydrocarbon as a solvent like hexane or pentane. And organolithium reagents are considered these days to be superior to Grignard reagents. A reaction is cleaner, that means there are fewer byproducts, and proceeds in a better yield. Otherwise, reaction outcome is the same. So organomagnesium compounds or Grignard reagents and organolithium compounds react with carbonyl compounds, and in general in most other reactions in essentially the same way. The only difference is that organolithium compounds are a little bit superior in terms of purity of reaction product and reaction yield. Now we are going to look at reactions of some organolithium and organomagnesium compounds. Before we do that, we should examine properties of these compounds first. So when we consider an organomagnesium compound, here is a typical example, vinyl magnesium bromide. Typically we write a formula where we show carbon-magnesium bond, because to us that's important bond. And then we simply show a magnesium bromide unit without indicating type of bond between magnesium and bromine. So that's common representation of organomagnesium compounds or Grignard reagents. But this is the actual structure. So actually carbon-magnesium bond is polar covalent bond, where carbon is the negative end of the dipole and magnesium is positive. Magnesium bromide bond is ionic bond, but that's of no interest to us, so we ignore that bond. And finally, this is actually how Grignard reagents react. They behave as if carbon-magnesium bond were ionic, and carbon is a nucleophile. So carbon behaves as if it carried full negative charge and has free electron pair. So when it comes to reaction mechanisms, that's what we do in reaction mechanisms. We assume that carbon has the electron pair and donates that electron pair to an electrophile. And similar to it, this is what organolithium compounds look like. So we have butyllithium. Butyllithium is represented as shown on the left. Actually, this is unfortunately in inverse order. So butyllithium is shown on the left. the actual structure is shown to the right, where carbon-lithium bond is polar covalent, just like carbon-magnesium. And again, just like carbon-magnesium bond, carbon-lithium bond behaves as if carbon were a carbanion, which means carbon behaves as if it had full electron pair, complete electron pair to itself and negative charge. Now, reactions, we are going to look at one type of substitution reactions, and that's ring opening of epoxide. So carbon-oxygen bond is broken and replaced by a carbon-carbon bond. This is a very important reaction because it replaces carbon heteroatom bond with carbon-carbon bond. So this reaction forms new carbon-carbon bond. It helps us establish skeleton of a molecule. And it's a common reaction that is used to extend carbon chain by 2 carbon atoms. So whenever an organolithium or organomagnesium compound reacts with epoxide, if it's simple epoxide, oxirane, then carbon chain is extended by 2 atoms, and upon protonation, product is alcohol. Reaction is SN2 reaction, and it involves backside attack on carbon-oxygen bond. So initial product is metal alkoxide, and then it is protonated to give the final product. If, as in the last third reaction here, epoxide is unsymmetrical epoxide, so it has a substituent on one of the carbon atoms of the oxirane ring, then reaction occurs at less substitute carbon atom. That's because it's SN2 reaction, and so less hindered atom of the epoxide reacts. Note that when it comes to organolithium and organo-Grignard reagents, alkenes, that means vinyl compounds, and aromatic compounds, benzene rings, react without any problems. In fact, they are very good reagents in these types of reactions. Organometallic compounds are very strong bases. In fact, they are among the strongest bases known. For that reason, they react readily with water, and water has to be excluded when they are prepared. If even a trace of moisture is present, it will react with organometallic compound, organomagnesium or organolithium compound, and replace metal with hydrogen. And so we end up going from very valuable organometallic compound to a very low cost alkene. So that's undesired reaction. But reaction could be exploited if we want to isotopically label a particular position on a carbon chain. So we can introduce deuterium in a particular position by doing reaction with deuterium oxide. One of the main uses of Grignard reagents and organolithium reagents is addition to aldehydes and ketones. That reaction also results in formation of new carbon-carbon bond. And in this first example, organomagnesium compound reacts in such a way that carbonyl carbon adds or reacts with carbon of the Grignard reagent to form new carbon-carbon bond, and intermediate is alkoxide. Upon protonation, product is tertiary alcohol. So as a general rule, ketones react to give tertiary alcohols as products. And here is another reaction, another example. It involves aldehyde instead of ketone and cyclopentyl magnesium bromide. This is just to show that cyclic compounds react just as well. And since carbonyl compound is an aldehyde, product is, upon protonation, secondary alcohol. So aldehydes give secondary alcohols as products. Then third example involves reaction of acetophenone with ethyl magnesium bromide, and again reaction of a ketone, so we get tertiary alcohol as a product. Final example, reaction with an aldehyde. So this would be 2-methyl propanol and reaction with phenyl magnesium bromide. And again, if this is an aldehyde, then product is secondary alcohol. In general, reaction with Grignard reagents or organolithium reagents tolerates double bond or double bonds very well. So in this compound, this carbonyl compound, so this would be 4-pentene 2-on. Double bond is unaffected. So only carbonyl compound reacts and double bond is unaffected. So reaction is chemoselective. That means it reacts with Grignard reagents react with carbonyl compound but leaves double bond intact. And of course double bond could be present in Grignard reagent. So we end up with product with 2 double bonds. So this shows value of these reagents, organometallic reagents, as double bonds can be present, and that's very important because they could be used in further manipulations of these compounds. Organolithium reagents react exactly the same way as Grignard reagents. I mentioned that already. The only difference is that reaction is much cleaner, so fewer byproducts, and reactions occur in much better yield. And so here is an example of benzaldehyde with ethyl lithium in hexane, and upon protonation again we get secondary alcohol. This would be 1-phenyl 1-propanol. Interestingly, carbon dioxide has 2 carbonyl groups. We may not look at carbon dioxide that way because it's an inorganic compound, but it does have 2 carbonyl groups. And so one of the 2 carbonyl groups can react with Grignard reagent or organolithium reagent. And reaction proceeds as expected, but because there are 2 carbonyl groups, 1 carbonyl group is preserved in the product. So upon protonation, we get corresponding carboxylic acid, and this carboxylic acid has 1 more carbon atom compared to starting organic compound. So this is a way to extend carbon chain by 1 atom. We have seen that before. Carbon chain can be extended by 2 carbon atoms by using epoxide, and this is a way epoxide to react with a Grignard reagent or organolithium reagent, and this is a way to extend carbon chain by 1 atom. So now you know how to extend carbon chain as needed by 1 or 2 carbon atoms, and we can repeat that sequence over and over again until we get carbon chain of desired length. And of course organolithium compound reacts the same way. So here we have pentyl lithium. Reaction with carbon dioxide gives hexanoic acid upon protonation. And so here is that's the reaction. Lithium dialkyl cuprates or Gilman reagents are very useful organic reagents. There are a number of organocopper reagents that are useful. Here we have listed 3 ordinary organocopper reagent on the left. In the middle, circled in yellow, is lithium dialkyl cuprate, and on the right, dilithium trialkyl cuprate. All of these have use in organic chemistry, in organic synthesis, but the middle one, lithium dialkyl cuprate, is used almost exclusively. And that's the one that is called Gilman reagent, after Gilman, of course, who discovered them. Gilman reagents are prepared in transmetallation reaction. We can use actually Grignard reagent, organomagnesium reagents to prepare Gilman reagent, but much more commonly we use organolithium reagents. So we need 2 equivalents of an organolithium reagent, as in this example ethyl lithium, and react it with copper salt. Most common copper 1 salts that are used are copper iodide and copper cyanide. Typical solvent is ether or THF, tetrahydrofuran. Ether means diethyl ether. And product is lithium dialkyl cuprate, in this case lithium diethyl cuprate, and byproduct is a lithium salt like lithium iodide or lithium cyanide. Usually those lithium salts don't affect reaction outcome and are not removed. They are left in the reaction mixture and reaction is carried out further. This reaction is transmetallation reaction because copper is much less reactive compared to active metals. And that's actually an advantage. That gives rise to particular use of Gilman reagents. Organometallic compounds have a nucleophilic carbon atom. So, for example, in this example highlighted in yellow, we have cyclohexyl magnesium bromide. And it would be really nice if we could use such a compound with nucleophilic carbon to react it with compound that contains an electrophilic carbon, like alkyl halide, in this case cyclopentyl bromide, to form new carbon-carbon bond. Problem is that when compound contains carbon-metal bond that is bound to an active metal, there is going to be halogen-metal exchange, because that's what active metals do. They readily undergo halogen-metal exchange. So if we mix either organolithium or organomagnesium compound with an alkyl halide, there will be halogen metal exchange as shown here. So some of the cyclohexyl magnesium bromide will react with cyclopentyl bromide, and product will be cyclohexyl bromide and cyclopentyl magnesium bromide. And some equilibrium mixture will be established with all these four compounds present. And then they will all react with each other, and we'll end up with all of these products, dicyclopentyl, cyclopentyl cyclohexane, and dicyclohexyl. So pretty much a pretty bad mixture that is more or less useless. So for that reason, organomagnesium and organolithium compounds cannot be used in these types of reactions. These are so-called coupling reactions. But organocopper compounds, Gilman reagents, are actually very useful. Since copper is not active metal, it doesn't undergo halogen metal exchange, and it is still a source of nucleophilic carbon. So carbon nucleophile from organocopper reagent will readily react with alkyl halide to form new carbon-carbon bond. So here we have an example of reaction of bromobenzene with lithium dimethyl cuprate, and product is toluene. Product is obtained in excellent yield, and there are no side products. Reaction is actually really useful, really robust, in that because of the low reactivity of copper, a number of other functional groups could be present, like double bonds. And in fact, double bonds could be present either in organocopper compound or in alkyl halide, in this case vinyl halide. So we have here vinylic compound attached to copper, or vinyl group attached to copper, and vinylic bromide. And again, carbon-carbon bond is formed, and product is actually a conjugated diene. From this you can tell that reaction mechanism is not an SN2 or anything like that. Reaction mechanism is rather complex and involves copper atom that complexes with alkyl halide, and then new carbon-carbon bond is formed. We don't cover details of the mechanism in a course like this. Organocopper compounds, because of their low reactivity, don't react with ordinary carbonyl compounds like aldehydes or ketones, which means that aldehyde or ketone group could be present elsewhere in the molecule and will not undergo reaction. This is obviously very useful if we want to form new carbon-carbon bond and carbonyl group is present elsewhere in the molecule. So here we have an example of chloroketone reacting with lithium dimethyl cuprate, and we end up with ketone with one more carbon atom. Chlorine is replaced by a methyl group. So very useful. Obviously, organolithium and organomagnesium compounds would have reacted with carbonyl group. If more than one carbon-halogen bond is present in the molecule, then all of those bonds are replaced by carbon nucleophiles. So in this case, dibromide is replaced with two methyl groups, and we end up with dimethyl compound. And note that three-membered ring is left unchanged. It doesn't open. So again, it shows utility of Gilman reagents. Gilman reagents react with epoxides the same way as organomagnesium or organolithium compounds. So reaction is SN2 with opening of the epoxide ring and formation of new carbon-carbon bond. This may not appear to be very useful because organolithium compounds give the same reaction. And of course, since we use organolithium compounds to prepare Gilman reagent, then why would we go through additional step to prepare organocopper reagent, Gilman reagent, when we can use organolithium reagent directly? And actually we wouldn't. For this reaction highlighted in yellow, we would actually use methyl lithium to get desired product. But we would use Gilman reagent if there is some sensitive group that would react with organolithium reagent if that sensitive group is present elsewhere in the molecule, as in this case where we have keto epoxide. So we have keto group and epoxide group, and of course we want only epoxide group to react. Organolithium compound would have reacted both with epoxide and a ketone, but organocopper compound only opens the epoxide ring and leaves ketone intact. sp carbon nucleophiles are acetylides and cyanides. They are readily available or easily prepared. So acetylide ions are easily prepared from terminal acetylenes. Of course, acetylene has to be terminal so that it has sp hybridized carbon-hydrogen bond, and such compounds are reacted with very strong bases. Strong base would be sodium hydride, or, as in this case, sodium amide. Sodium amide could be used in liquid ammonia as a solvent, or we could use different solvents. Product is sodium acetylide, and sodium acetylide has nucleophilic carbon. Such nucleophiles readily react with, for example, carbonyl compounds, and they react as expected. They form new carbon-carbon bond. New carbon-carbon bond is formed between nucleophilic carbon of the acetylide and electrophilic carbon of the carbonyl compound, in this case ketone. Initial product is alkoxide, sodium alkoxide, and upon protonation we obtain corresponding alcohol. This reaction works very well. Compounds are really easy to prepare. Acetylide ions are easy to prepare. The only problem is that triple bond is frequently not needed in the final product. And so we may have to carry additional reactions to get rid of it. So we may have to carry out hydrogenation, for example, to convert it to alkene or alkane. Still, because of the ease and low expense of the reaction, this reaction is frequently used in industry and also used in academic laboratories. Another sp hybridized carbon nucleophile is cyanide ion, and cyanide ion is commercially available in form of various cyanides. Most commonly used cyanide is potassium cyanide, and copper cyanide is occasionally used. So cyanide, of course, contains carbon nucleophile and readily adds to, for example, carbonyl compound to form intermediate alkoxide, and in this case protonation step is actually not necessary, because in the reaction mixture small amount of hydrogen cyanide is present. It acts as a proton donor and protonates the intermediate alkoxide to give the final alcohol, final cyanoalcohol as the product. This reaction is both important and, so this is final alcohol as a product, it's both important and interesting because the reaction is actually reversible. This is one of the very few reactions that form carbon-carbon bond that is reversible. So in presence of a base, hydroxide group is deprotonated to give alkoxide anion, and that alkoxide anion actually expels nitrile group, cyanide group, and reforms the ketone. So one of the very few reactions that is reversible. This is actually important because if we want to protect carbonyl group, we can use this reaction. So we can add nitrile group, cyano group to carbonyl group, carry out reaction elsewhere in the molecule, and then remove nitrile group and have intact carbonyl. Finally, this reaction has been exploited in Strecker synthesis of amino acids. So reaction of carbonyl compound with mixture of potassium cyanide and ammonium chloride results in this aminonitrile. So reaction involves first addition of cyanide to carbonyl group as shown above, and then intermediate alkoxide is protonated. It's actually, you can figure out that second step on your own. It's actually SN2 reaction. So intermediate alkoxide is protonated twice to give oxonium ion. That oxonium ion is replaced by ammonia to give ammonium compound, which is deprotonated to give aminonitrile. And finally, acid catalyzed hydrolysis of the nitrile group gives corresponding amino acid. This is a very good method to prepare synthetic amino acids. The only drawback is that these amino acids are not chiral, they are racemic mixtures. And of course, naturally occurring amino acids are single enantiomers. And finally, we have a different type of carbon nucleophiles that don't contain carbon-metal bond. So they are not organometallic reagents. They are phosphonium ylides or Wittig reagents. They contain carbon-phosphorus bonds, and as you will see, ylides are compounds that contain charge separation, have charge separation. Here highlighted in yellow is typical ylide, methyl triphenylphosphonium methyl ylide, and you see two resonance structures for it. So resonance structure on the left shows charge separation. Ylids are prepared in an SN2 reaction. We use typically triphenyl phosphine. Phenyl groups are needed because, unlike alkyl groups, they do not form carbon-phosphorus ylid bond, and so they don't interfere with further reactions. They simply serve as ligands on phosphorus to satisfy phosphorus valence, but they don't participate in further reaction. We can't have alkyl groups on phosphorus. So in an SN2 reaction, an alkyl halide reacts with triphenylphosphine to give this phosphonium salt. Phosphonium salt has positively charged phosphorus, but actually it's alkyl carbon that is attached to phosphorus that is electron deficient. And that means that hydrogens attached to that carbon are slightly acidic. If we use very strong base, it has to be exceptionally strong base like butyl lithium. So if you use such strong base, that carbon could be deprotonated. And as a result of deprotonation, a phosphonium ylid is formed. And again, the same two resonance structures as shown above are shown here. In the top example, we had methyl ylid, now ethyl. Ylids readily react with carbonyl compounds to give alkenes as final products. In the first step, ylids are actually Zwitter ions, and Zwitter ion is a species that includes both positive and negative charges in the same molecule. So an ylid is a Zwitter ion that has charges on the neighboring, on adjacent atoms. So carbon and phosphorus are next to each other, so that makes it ylid. Carbon is the nucleophile, obviously it has negative charge and free electron pair. So nucleophilic carbon adds to carbonyl carbon to form a new carbon-carbon bond. The resulting product, so that's the reaction, the resulting product is a betaine. Betaine is another type of Zwitter ion. So ylids and betaines are different types of Zwitter ion. Betaine is a Zwitter ion that has charges on non-adjacent carbon atoms. So as you can see, oxygen and phosphorus are not next to each other. Oxygen and phosphorus form very strong bonds. And in this case, of course, we have electrophilic phosphorus and nucleophilic oxygen. So they form a bond to each other. And that's actually what makes this reaction thermodynamically favorable. Because phosphorus and oxygen forms bonds so readily, and those bonds are very strong bonds, organic reactions proceed in such a way to make maximum number of phosphorus-oxygen bonds. And in fact, we often had that as empirical rule in organic chemistry, that any organic reaction involving phosphorus will proceed in such a way to produce maximum number of, or to result in maximum number of phosphorus-oxygen bonds. So this next step, in this next step, betaine undergoes cyclization to give a four-membered ring called oxaphosphatane. Oxaphosphatane is unstable and actually could make an additional phosphorus-oxygen bond by internal rearrangement of bonds as shown here by arrows. And so we end up with reaction products. Reaction product is alkene and triphenylphosphine oxide. And actually it's triphenylphosphine oxide that is the stable compound, and it makes this reaction possible and this reaction thermodynamically feasible. But to us that's a byproduct, we actually discard it, and to us alkene is of interest. So overall product of Wittig reaction is an alkene, where a new carbon-carbon double bond is formed. So unlike previous organometallic reactions, where reaction of carbon nucleophile with carbon electrophile produced carbon-carbon single bond, here reaction of carbon nucleophile with carbon electrophile produces carbon-carbon double bond. And here are some more examples. Note how cyclic compounds produce exocyclic double bonds. Exocyclic bonds are rather unstable, and trying to do these reactions by other methods probably wouldn't work, because these bonds would have rearranged into endocyclic double bonds. So Wittig reaction is one of the best methods to make selectively double bonds in the position, in desired position. A double bond will always be formed between ylid carbon and carbonyl carbon. It doesn't matter what is the rest in the molecule, what are the other structural elements in the molecule. So in this case, double bond will be exocyclic. There are no rearrangements, so double bond will not be rearranging to end up inside the ring, which will be more stable double bond. Double bonds using simple triphenyl phosphonium ylides are cis double bonds, which is another unique feature of Wittig reactions. Because cis double bonds are less stable than trans, they are more difficult to prepare. A lot of natural products contain cis double bonds, so those are desired double bonds, and we would like to have good methods to prepare them. There are relatively few methods to prepare them, and this is one of the rather selective methods. So using simple triphenyl phosphonium ylide and reaction with an aldehyde, it has to be aldehyde, results in formation of a cis double bond. If it's a ketone, then of course we get mixture of isomers, because ketone has two alkyl groups, and we usually end up with mixture of isomers. If we use different type of ylide, so-called stabilized ylide, one that has oxygen atoms on phosphorus, it's a little bit different type of ylide. That one has carbon, negatively charged carbon, nucleophilic carbon, stabilized to resonance with oxygen atoms on phosphorus. Such ylide reacts a little bit differently, and reaction with aldehyde results in formation of trans double bond. So stabilized ylide, remember that stabilized ylide is one that contains oxygen atoms on phosphorus, results in formation of trans double bond. So you need to know stereochemistry of the reaction. You need to know when Wittig reaction results in formation of cis, and when it results in formation of a trans double bond. And this completes this part of the chapter on carbon nucleophiles. Next, in the final part of this chapter, we will be covering oxygen and nitrogen nucleophiles.